Okay, so this was the research paper which introduced the ACT policy to the world. It came out in the year 2023, which is almost more than 2.5 years from this point of time. And it really was an amazing paper from several different points of views. We'll look at that. So one of the authors in this paper, his name is Sergey Levine, and I follow him a lot on different channels. He's one of the pioneers in modern robot learning, and recently he has last year co-founded a company called Physical Intelligence, where their objective is to build general purpose robot policies. Instead of training one robot for a specific action, their aim is to build a policy which is general purpose, which can work for a wide range of tasks without having to train the robot again and again. Okay, so let's go to our Miro board and understand it. Now, first, let's have a broader look at why this policy gained attention in the first place. So, the reason why it gained attention was for the first time, this paper showed that AI policies can be implemented in low cost hardwares for achieving complex tasks. Previously, before this paper came out, people used to use complex robotic arms, which were very costly and non-affordable for people who wanted to try out these policies. So the cost was on the order of magnitude of lakhs of US dollars. And it was impossible for a small scale research lab to try out AI policies on low cost hardware. But this paper showed that it can be done. And this name Aloha, you might hear about in a lot of other papers also. So it means a low cost open source hardware system for bimanual teleoperation. And some of the tasks which were completed using the ACT policy were very interesting. You can see it's called bimanual because there are two arms. This is the first arm and this is the second arm. So in this task, the two arms are working in collaboration to open a Ziploc bag. So opening a zip is something which requires pretty fine-grained manipulation, right? It is not something which is very easy. The second task is the slot battery, where you have to basically pick this battery and place it in this slot, just as we have in remotes and other electronic devices. So one robot is holding the remote and other robot is picking the battery and putting it in the slot. Then the third one is opening the cup, like the lid of the cup. And similarly, there were a lot of tasks which they demonstrated can be achieved. And compared to other policies, the gains which ACT had were very impressive. You can see these numbers. They are very high compared to all the other numbers that you see previously. Many of these are in fact zero. And two of these are simulations and two of these are real. So let's focus on these, the Ziploc and the slot battery. So almost all other methods completely fail in these tasks. But the ACT policy achieves a lot of, achieves a higher accuracy in these tasks. And this is one of the reasons why it caught the attention of the robotics community. There were a lot of innovations on the hardware side as well. They were able to manage this entire setup in a cost of $20,000. Now that might seem high to you compared to the SO101 robot, which is almost 100 times cheaper. Uh, yeah, I understand there is some internet connectivity issue, I think, today in my location, but I hope you are able to hear now properly. Let me try switching to a different Wi-Fi and see. Okay, so apart from the innovations on the software side, they did a lot of innovations in the hardware also, and they achieved this entire setup in the total cost of $20,000, uh, which they have given somewhere at the bottom, I think. Okay, is the voice is the voice clear now? I have tried switching to a different Wi-Fi. I hope this is better than the previous. Okay, fine. So let us go back to our previous point of hardware. So they arranged this entire setup within a cost of $20,000, and they have given a breakup here. Yeah. So this was the overall budget, and this included a total of four arms, two leader arms and two follower arms. If you see in this setup, there are four arms, one, two, three, four, and two of them are leader arms and two arms are follower arms. So if you have purchased the SO101 kit, you get two robots within that kit. One of them is the leader robot and one of them is the follower robot. Here, since they are doing a bimanual operations, they have 2 into 2, that is four number of robots totally. And each robot costs around $3,300. So you multiply that by 4, and the remaining cost is printing of these arms, the table, then purchasing the webcams. They have used a total of three cameras, or rather four cameras. There is a top camera which is mounted over here. There is a camera in the front, and there are two cameras which are mounted on the wrist of the robot. Now, these cameras come along with the SO101 robot. So, this is something that even we will do when we implement our policies. But the number of cameras that we should use are optional. It really depends on which setting works the best. I think the reason they have used two cameras here is if you look at the front camera, you miss out the total spatial information of the operation. But if you have a top camera, it allows you to capture the entire three-dimensional geometry of the objects. So there was a lot of innovation in the hardware side, but today we are going to mostly focus on the the innovations on the software side. And there are three things that we are going to learn today, which make this policy unique. The first is it uses a conditional variational autoencoder. The second is it uses a DETR inspired transformer decoder. And the third is it uses action chunking. This action chunking is something which is now common in a lot of other modern robot policies. So it is very important for us to understand why the action chunking is important and how it helps us to control our robot. So we are going to explain all of this in detail, and we will understand these three software innovations really closely. Now, the reason why we are understanding the software side so much is once you understand this, it sets up a perfect foundation for you to later tweak this policy as you require for your own research problem statements, or even if you want to understand any complex policy, it becomes a very good starting point. Now, in the last lecture, I had posed a question to all of you. The question was, we had looked at variational autoencoders separately. Okay, we had looked at transformers encoder and decoder separately. And I have been talking about this a lot, that in act policy, we are going to look at how both of these are used in parallel or used together. And we are going to address this question today. So the way I am going to take this lecture is, I'm not going to tell you the entire architecture in the first go, but rather we are going to build it step by step so that we understand the different pieces of the puzzle and their importance in the puzzle. If I showed you the entire assembled puzzle at the start itself, then you will not be able to understand or appreciate why that piece exists in the puzzle in the first place. Okay, so let us understand from the very first principles. What we want to do is, at the end of it, we want to predict the distribution of the variation of the joint angles given the state of the robot. Now, what does this mean? Let's say I have a robot which is disassembled right now in my camera. So let's say this is the state of the robot. So what do I mean by state of the robot? I mean the observation consists of 6 angles because there are 6 degrees of freedom. Now, given this state of the robot, what is the next action which the robot should perform? That is, what should be the 6 joint angles in the next time step? So, given the 6 observations, we want to map these observations to the actions. Now, let's revisit the variational autoencoder architecture. In the variational autoencoder, we started with a bunch of images. Then we had an encoder which compressed these images in a latent space. And then we had a decoder which took these images back into the original space. So here we were trying to learn the probability distribution of these original images. That is P data of X. Now think about this same setup, but applied to our robot. We do not have just images at the moment, but for now, just imagine that we only have the angles of the 6 degrees of freedom. So essentially, we want to predict the probability distribution of the joint angles. This is what we want to predict in our robotic setting. So we do not have images right now. Imagine we only have proprioceptive data. That is, we have information on how the joint angles are varying. Let's say we have collected 100 demonstrations. So we want to predict using this variational autoencoder. Given these 100 demonstrations, can I learn how each individual joints are moving? That is all I'm trying to do in this case. So if we try to map it in this encoder decoder architecture, what is passed to the encoder is the 6 joint angles. The encoder encodes it in the latent space and then we decode it back. Okay, so this is what we are trying to learn. Now, the important thing here is in images, if you think closely, if I showed images of handwritten digits, our VAE learned to sample from these handwritten digits. So sometimes I would sample 1, sometimes I would sample 2, sometimes I would sample 3, etc. So if we just use this setup, then our decoder would just predict actions which would belong to that probability distribution. But is that what we want? We do not want to predict the actions randomly. That doesn't make sense. We want to predict the action given the current observation. So the action should only be predicted for a given observation. So even if we manage to train the above variational encoder, at the end of it, we will get different actions, which are the joint configuration sampled from the action space. So the robot is going to move in a very random direction. So we want to model the distribution of the joints given the current state of the robot. So we don't just want to sample from the distribution of the joints randomly, but we want to sample from the distribution given the current observation. So now what we will do is we will modify the architecture version 0 to architecture version 1, in which the only difference is that we are passing the information about the joints as well as the action. So the observation as well as the actions to the encoder and also to the decoder. So here don't get confused between this ST and AT. ST is the current joint configuration and AT represents the joint configuration at the next time step. Now, in case you are trying to imagine how this distribution of actions look like, I have given a simple plot here, this is just a schematic. So this is what we are trying to predict. There are 6 joint angles, so you can forget about this. There are 6 joint angles, J1, J2, J3, J4, J5, J6. Every joint angle is going to have some distribution. Now, if we do not condition it on the current observations, we will randomly sample 6 joint angles. But that is not what we want. We want to sample from this given the current observation, which is why we are also passing these observations along with the actions to the encoder and the decoder. Okay, so this is the first step where we have reached till architecture number 1. Now, as we have seen before, the observations do not just consist of the proprioceptive data, but they also consist of the image data. Why is this the case? We had looked at an example where if you only learn the proprioceptive data, let's say you are pouring milk in a coffee, you will learn the action of pouring milk, but if you do not know exactly where the cup is placed, how will you pour the milk in the right place? That is why you need access to the images also. And that's why in the paper you saw there are 3 cameras which are mounted here. These cameras are looking at the environment around it and collecting images from the environment. So we need to modify this architecture number 1 in such a way that not just the proprioceptive data, which is the joint angles, is passed to the encoder, but along with the joint angles, we also pass the images. So this way we go to architecture number 2, where along with the 6 angles, we also pass the images from the 4 cameras. Why are there 4 cameras? Because there are 2 wrist cameras, there is a top camera and there is a front camera. So there are 4 images which we have at every single time step, which are passed to the encoder. And the same information is also passed to the decoder. So what are we essentially trying to do in this decoding stage? Imagine that you have a robot like this, which I am holding in my hand right now, and you want to predict the action at the next time step, right? Now, the action at the next time step depends on the current observation, which is the proparaperceptive data, and it also depends on the four images which are collected by the four cameras at this time step. That is why this is passed to the encoder, to the decoder, sorry. Okay, so now let's say to understand the frequency at which these images are passed to the encoder, if we are recording the data at 30 frames per second, then for every second of recording, we have 30 time steps. So if you have recorded a, let's say, observation or recorded a, an episode of 10 seconds, you would collect 30 into 10, that is 300 time steps of data. Okay, so we have reached till architecture version 2, where we are using just a variational autoencoder. So far, we have not even touched transformers yet. But this time we are using a conditional variational autoencoder because we want to predict the actions conditioned on the current observations, which is the proprioceptive data as well as the data from the camera. Now we have to think deeply here. This looks like a good architecture, but will this work in practice? Why was this not the architecture version that the authors of the ACT paper went ahead with? Can anyone think about it? It looks like we have solved the problem, right? We have learned to predict the actions of the robot given the current state. So Rajesh says that the motion of the robot will be jerky. Okay. Anyone else wants to answer? Okay. Think about it this way. Okay, let's understand the output. Imagine that you have recorded an episode in which you are picking a ball and you are placing it. Yeah, Yashwant says VAE has limitation outputting blurred images. But there is something more interesting here which we need to understand. For handwritten images, what we did was we gave an image of input 3 and we sampled 3 from the VAE. So we are just predicting one sample at a time. The difference between this and our application is here we are predicting a sequence of actions. So the action at the first time step is A0, action at the second time step is A1. So let's say you're collecting a data at 30 frames per second and you're collecting 10 second of data, there will be 300 time steps. So you have 300 action or A0 to A299, which is coming in a sequence. Now your variational autoencoder is not just responsible for predicting one action at a time, but this sequence should be followed, right? After A0, A1 should come. After A1, A2 should come, etc. So how will you learn this interdependence between the actions in a sequence? This almost looks like a next token prediction in an LLM. If you look at it closely, LLM also predicts one action at a time. So let's say my output is the image is blurry, let's say. So this is the current observation. For this observation, this is the action, the image. Now at this stage, this becomes the observation and this becomes the action, the image or is becomes the action. Then this becomes the observation and this becomes the action. So essentially what I'm trying to say is this cannot just be modeled as a conditional VAE because we are not just predicting single actions, but there are sequence of actions and they have some relation between each other, which we can leverage in our architecture. So let's build upon that intuition and go towards architecture version 3. First, we will start with the encoder. Now, the first thing that comes to mind with respect to the encoder architecture is, let's look at the encoder architecture. Remember in the handwritten digit example, we went ahead with an architecture which was a simple multi-layer perceptron or a simple neural network. Now here also let's start with that intuition. Why can't we just go with an MLP? So this is the first architecture which comes to mind. These are the observations. These are the actions. And you concatenate them together. You pass them through an MLP, and then you predict the latent vector, which is Z. So if you are trying to design the architecture for the encoder, I might come up with this when I first look at it. But the problem here is that this is a good start, but there is one major problem, that is this does not leverage that there is a sequence of observations which is coming in to the encoder and there is some relation between this sequence. So we are first getting observation 1, then we are getting observation 2, then we are getting observation 3, etc. But all of these observations are linked to each other because they are coming in a sequence. Okay, so let's try to understand how can we modify this architecture so that we shift from an MLP and instead of an MLP we use a transformer encoder. So we don't use a neural network, but rather we use a transformer architecture for our encoder because we want to leverage these sequence of observations which are coming in. Now, this is the first architectural change, but this also brings us to a very important concept, and that concept is that of action chunking. So, the name action chunking with transformers comes because I will again explain this later, but I just want to explain this at the top. Okay, so in a traditional LLM, you pass a state and you get an action which is one token at a time. And you can do that for a robot also, where let's say this is the policy of the robot, and you have an observation which is the current state of the robot and the images. And for this observation, you predict an action, which is the joint angles at the next step. Now, what people observed is that if you predict one single action at every time step, it leads to a motion which is very jerky. because you're predicting one action, then you're again predicting one action. So there is a jerkiness in the output. Another issue with this is if one action is wrong, if one predicted action is wrong, the action next, the action which comes after that also becomes wrong. So the error keeps on getting compounded. So this is called as compounding problem. Instead of that, what this paper said is, instead of just predicting one action, why don't you predict a chunk of actions at a time? So why don't you predict a chunk of, let's say, 10 time steps? Instead of predicting the action at only the next time step, why don't you predict the action at 10 time steps? So this will smooth out your motion, right? Because you're not predicting one action at a time, but you're predicting a chunk. It's almost as if you can imagine, let's say you're walking, and if you take just one step at a time, your motion will be very abrupt. But instead of that, you take 10 steps at a time, you will cover that same distance very smoothly. And the errors will not get compounded here because let's say you're walking and your first step is false, then the next step becomes even more like it drifts even more, and the drift keeps on getting compounded. But here you are reducing the compounding by 10 times because you're calculating 10 steps at one time. So that influence of the drift at every time step gets minimized. So in action chunking with transformers, one of the major contributions on the software side is you predict a chunk of actions. And that is why here I have given 6 actions which are passed as an input to the encoder. Rajesh has a question, why don't we do the same with LLMs? In fact, there is a transformer called detection transformer which does that. I will come to that shortly, but this idea has been explored for LLMs as well. Okay, so now what you pass to the encoder is you don't just want to learn the distribution of one action, right? In the variational autoencoder, you want to learn the probability distribution of 10 actions or a chunk of actions. That's why you pass all these actions as an input to the encoder. The question is, how do we decide the size of the chunk? That's a very interesting question. And in fact, there are a lot of ablation studies they have conducted in the paper where they decide the right chunk. If you decide a chunk which is too high, then your inference becomes slow and you do get some jerkiness because it takes some time to infer. At the same time, if your chunk is very low, then you lose all the advantages of doing action chunking in the first place. In the paper, they have used a chunk size of 10, I think. Let's see in the hyperparameter section. Yeah, here, if you look at it, chunk size is 100. They have used 100 time steps. So the horizon is like you're looking 100 time steps in the future. You're not looking at one time step in the future. So the concept is actually simple. It's not complex. It's just that it's very novel, and people who have not heard about this before, uh, this is something which is very novel. We will understand how we modify the decoder so that it predicts 10 actions at a time instead of one single action. Okay, so now after this, it we come to architecture version 3, which is instead of using MLP, we are using the transformer now. And it should make sense to you that whenever we have any sequence involved, we should definitely use an encoder which understands how to represent the sequence together. And that is exactly why the transformer encoder is used. One thing which the encoder will do, which an MLP cannot do, is since you have a sequence of k future actions, let's say there are these 4 actions which I'm predicting. If I'm just using an MLP, it will not be able to understand the relation between these actions. And the attention mechanism is designed to find relations between different tokens in a sequence. So it becomes an ideal mechanism to analyze sequences. Yes, so we will be using self-attention in this architecture. Okay, so now we will be revising a bit about transformer encoder. We have already covered this in the last lecture, but I want to again make sure that all of us understand what is exactly happening inside this transformer encoder, but from the point of view of robotics data. So the transformer encoder has this architecture. We pass the current state, which is the information about the joint angles. Along with this, we also pass the chunk of actions, which depends on your chunk size. For now, let's assume that the chunk is 10. So how many tokens you have here? You have one token for the state and you have 10 tokens for the actions. So you have a total of 11 tokens which you are passing as an input to the encoder. Okay. Now the first step which happens in the encoder is it embeds all these tokens. So the first step is tokenization as and embedding. So every token gets a uniform. 11 tokens, all of these tokens get a uniform. Then they are passed through the transformer layer. And finally, we get a context vector for all of them. Now, again, here we come with the same problem that we will get 11 context vectors out of it. Which context vector shall we choose for our latent vector? And we had looked at this exact same problem when we were discussing about vision transformers. And there we discussed we can add a token which is a CLS token. So a CLS token is something which is initially set as a random variable. It has random values, but we will generate a context vector for a CLS token which will hold the summary of the entire sequence of actions. And then whatever is there in the CLS token will be our latent vector. So whenever you're thinking about an architecture from scratch and you use a transformer encoder, and you want a place where you hold the summary of that entire input, then you will use a CLS token in that case. And this is something which we had looked at. It's the same architecture being followed in vision transformers as well. Okay, so now we will dive a bit deeper and understand what happens within these attention layers. So let's try to visualize this. Okay, so this is a high level overview that the state and the action chunk are passed as an input. And then let's understand what our attention layer is trying to do. So we go to the next step. So now I'm going to explain the individual steps in the transformer encoder. As I said, the first step is the embedding process. So what do you have to embed? You have to embed the CLS token, which is just a learnable parameter. We have to embed the joints. So here I have given 6 two values, but for our case, there will be six values in the joints data. And then you embed this using a linear layer and positional embedding, and you get a final embedding over here. Similar embeddings you do for actions, but you don't have a single action right now. You have a chunk of actions. So you do the embedding for action 1, action 2, and action 3. Here in this example, I have chosen a chunk size of 3. So you have embedded the joints and you have embedded the actions. Now let's go to the next step and understand what happens in the attention mechanism. So let's select the joints. Now, if you remember, the attention is calculated by doing a product of, or a dot product rather, of queries and keys. Now here, the query vector is fixed, which is the joints, and the key vector is shown here. There are 5 key vectors. One is the CLS token, one is the joints itself, one is the first action, second action, third action. And you do a dot product between this query vector and key vector, and you get a final number, which is your attention score. Similarly, we do it for these actions, and we do the same thing for the CLS token also. Whatever is happening in the CLS token is very important to us, because finally we will only be looking at the output of the CLS token itself. And here you can see why the CLS token is called as something which holds the summary of the entire input, because the CLS token query attends to all the keys. So it's understanding how the different joints and actions are related to each other. So intuitively, what is happening in this transformer encoder is you are teaching the encoder to understand the different ways in which your robot is moving. Remember, you are not passing image data here anywhere. You are only looking at the proparaperceptive data, and you're trying to understand for different ways of moving the arm, which has a different distribution of the joints and the actions, the chunk of actions. Can I compress all that information into a single latent vector? Uh, I hope all of you listened up until this point where we calculated the context vectors for all these tokens. Now, what we are interested in is we are interested in the context vector only for the CLS token. So now we only look at this context vector, and we sample from it to find the latent variable. Okay, so if let's go back. If you only heard till the attention maths. Okay, so now what happens in the attention, the self-attention layer is that for every token, we generate a query vector and a key vector. And we do a dot product between the query and the key to find the attention scores for every token. And then once those attention scores are found, we multiply each attention score with the value vectors to find the context vector for all the tokens. So here I have given the context vectors for the CLS token, the joints, and all the actions. But all we are interested in is the context vector for the CLS token. There is another step here, which is of the multi-layer feed forward network, but for simplicity, I have not shown that over here. So after the attention layer, we pass the tokens through a feed forward neural network. And then we only look at the context vector for the CLS token. That's it. And then this is projected into a mean and a variance so that we can generate the value for the latent variable Z. This is exactly how the transformer encoder is set up. And you can see that the reason why we are using the transformer is because we want to learn the interactions in the sequence of these actions in which we are forming a chunk. A normal multi-layer perceptron would not be able to understand these interactions with the sequence. Okay. Now, let's quickly recap what we have done in the transformer encoder. In the transformer encoder, we are passing the current observation, which is the information about the joints of the robot angles. And we are passing the next set of actions, which are K, which is also called as the chunk size. The objective is to take all this information and encode it in a latent variable. But we do not use a simple multi-layer perceptron here, which we could use, but we do not use it because we want to understand the relation between these different actions since they are coming in a sequence. And because of that, we use a transformer architecture to encode all this information in a single latent variable. In practice, we do not pass this image data to the encoder, but we only pass the information about the proprioceptive data. So the encoder is only learning about the different trajectories in which your arm is moving. It has no information about the images. So it is also called as a style variable because it is learning different ways in which your robot is being moved to perform that specific action. And then what is happening inside the encoder is first the current state and the action chunk are tokenized. In this process, for each state and action vector, these embedding vectors are then passed through the subsequent layers. The most important layer here is the attention layer, which understands the relationship between each token and attention scores are generated. And the context vectors are calculated only for the CLS token because this is the token which holds a summary. And this is what we'll use to generate the latent variable. Okay, so now before we move on to the decoder part of this entire story, I will take a break and whatever questions you have, I will answer those questions. And then after that, we will move to the action chunking with transformers decoder. So let me stop sharing my screen and let us discuss about. First, we'll discuss only about the encoder and we'll try to understand if we really understand why the encoder works in the first place and the different components within the encoder. So I will stop sharing my screen, and if you have any questions, you can post in the chat or you can unmute yourself and ask the questions.
Um, Hi, sir, Vishaka here. So I don't have that much knowledge about hardware and robotics, right? And then this action and observation, right? These are the two things. So how I'm visualizing, like, if there is a uh,
Uh,
change in the angle, what will happen next? So this is how I'm visualizing, but I'm unable to connect
okay.
that thing
Yeah,
with the
that is
encoder.
that is very interesting question actually. So observations and actions is something which all of us should very deeply understand because that is exactly what is happening within the architecture itself. Now, let's take a simple example. If we are trying to learn the relationship between, let's say, on the x-axis, we have number of hours of study for a student, and on the y-axis, we have the marks. So the observation is the hours of study and the actions or the output is the marks. And we can fit a regression line to map the input to the output. Now here we are doing something very similar. Here the observation is the current state of the robot, which is the information about the joint angles. So there are 6 entries in the observation. Okay. And for every observation, there is an action, which are again 6 entries, which are the observation at the next time step. So the difference between observation and action is only for one time step. Otherwise, the information is only coming from the joint angles in both the cases. Now here what we are trying to learn, we are trying to learn the mapping between the observation and the action. Now, instead of just learning the mapping between the observation and one action, we are trying to learn the mapping between observation and 10 actions in the future. Okay, so observation and action, and we are trying to learn the mapping and how the observation and action are related. Now, what the encoder is trying to do is, our first discussion of the encoder, it started with this way. Let's say all of us are in a class, right? And all of us are told to write the word hello. We will write it in different ways. Some of you will be neat, some of you will be messy, some of you will write it in a way which is slanting to the right. Some of us will write it in a way slanting towards the left. Now, all of this will be the hidden factors of variation, which influence the way in which we are writing the word hello. Now, if we compress this information or capture it so that we understand these hidden factors of variation, which are also called as the latent variables. So if we have only 2 latent variables, which is the neatness and the slanting. So for each of your handwriting, I can map that to a latent variable, because all of us will have different neatness and different slant angle. Now here we are doing something which is very similar. Instead of the handwriting samples, we are given the observations and the action pair. And these observation and actions pairs, we are mapping to a latent variable. So in other words, we are trying to understand what are the hidden factors of variations beneath these observation and action pairs. Or to simplify it even further, controlling the robot. Or we have collected 100 demonstrations of picking an object and placing it somewhere. So these 100 people are going to have different styles of picking the robot, right? Now, these styles are what we are encoding in the latent variable. Someone will pick it in a larger arc. Someone will maybe just, the trajectory will be horizontal. So there are these different styles of picking and placing the cube. These are the different styles which we are trying to learn in the latent variable. Now you might say that why are we introducing this latent variable? Why don't we do something like regression where you directly learn the mapping between observation to actions? The problem with that is regression does not take care into account multiple modes of solving the same problem. So picking and placing, there might be 15 ways to pick and place, right? All of them are correct. Regression will only end up taking an average of all these 15 ways. We do not want to take an average. We want something which can understand there are 15 different ways and pick one way wherever possible. That is what is encoded in the latent variable. If I pick one value of the latent variable, let's say 0.2, maybe I'll pick an arc which is like this. If I pick another value, I will pick an arc which is going straight. So the latent variable encodes the different styles of controlling the robot for whatever task which we are planning to complete. So in this example, and the example which we are taking, which we are going to take in subsequent classes, is the pick and place operation.
Yes, got it, sir. And then one observation contains 6 angles and 6 observation. Sorry, 6 action, isn't it? No.
Six angles. One observation contains 6 angles.
Uh, yeah, got it. Thank you.
Yeah.
So what will be the initial state during inference? Because if we are taking action chunk as 100, because initially we don't have any 100 actions for the robot.
Yeah. Okay. So during inference, we do not need the actions. We are predicting the actions. So during inference, what will happen is first the observation will be collected. I will come to that, but here during inference, the observation is not just the joint angles, but also the images collected from the camera. That will be the observation. And given that observation, we are trying to predict the action, which is the 6 angles for the next 10 time steps. Then we again collect the observation, again we predict the action, and we keep on doing it. So to start the inference process, we only need the observations and the joint angles. That's it. We do not need the actions to start with. We are predicting the actions.
So it will be randomly initialized or zero initialized as actions for the first time. Because the dimensionality we cannot change.
Okay. No, for inference, we do not need to initialize the action. For training, we already have the actions. For inference, we do not need to visualize the action or have the actions.
Okay.
All we need to have is the observations. Then the action will be predicted. Then again, we need to have the observation. Again, the action will be predicted.
Understood.
Is there any question? If let's try to boil it down so that it becomes very simple. Uh, so at the end of this lecture, if someone asks you what does a transformer encoder do in the act, you will answer in such a way that, let's say, we are trying to do a pick and place operation, and there are multiple ways of picking an object and placing it over to any location. Now we want to capture all these different ways of picking and placing in a style variable so that we do not lose out on any information. That is exactly what the encoder is doing. The encoder is understanding all the different modalities of picking and placing the object. So that is all we are finally doing in the transformer encoder. Why the transformer is used is because here there is a sequence of action. If we only had one action, then I don't think there is a need for a transformer at all in the transformer encoder or in the variational autoencoder. In the encoder part of it, we could have simply used an MLP. So I was saying that in the paper, they have conducted an ablation study in which they have compared two methods. In the first method, we only have the decoder, and in the second method, we have the encoder and the decoder both. So it turns out that if we remove this transformer encoder, it significantly hampers the accuracy. Let me show that ablation study to you so that it will become clear. Yeah, so here, if you look at this section of the paper over here, yeah, we train ACT with the CVAE objective, which is conditional variation autoencoder, to model human demonstrations which can be noisy and contain multimodal behavior. And in this section, we compare the ACT without the CVAE objective also. And if you look at this comparison, so you can see this no CVAE, it performs 33% lower accuracy compared to with CVAE. That is why having an encoder which understands the noisy way in which humans can collect the data, the same task can be done in many different ways, is very important. I think this is one of the biggest achievements of modern robot learning, because if you look at classical robotics learns a single way of accomplishing a task. It does not learn these different ways in which the same task can be completed. Because for that, we will first of all need a probabilistic approach. We cannot do it with a deterministic policy. And secondly, we need something which can understand the variations in the data set very well, which artificial intelligence is very good at. So using a conditional variational autoencoder was one of the main highlights of this work, along with the second highlight that they use this concept of action chunking. And they have a very nice paragraph in this paper where they say that action chunking is a concept in psychology. So it's inspired from psychology that describes how sequences of actions are grouped together as a chunk and executed as a unit. I tried to find this paper which is written in this article 35, but I could not find this link to psychology. If any one of you finds a link, then please share it. I did not create the Discord group last time. I will create it after this lecture. But please share it with us. I'm also very interested to see how this is inspired from psychology. Okay, so now let's go to the next part of this architecture, which is the decoder. The decoder is very important for us to understand because the decoder is the part of the architecture which will be making the final predictions. So we need to understand how the decoder exactly looks like. Okay, so if we start from first principles, we want our ACT decoder to do something like this. The decoder will take the latent variable as an input. Just a second. Okay, the decoder will take the latent variable as an input and it will take these 6 time steps also as an input, which is to tell the decoder, okay, which time step you are at currently. And then this will be fast and we will predict the set of 6 actions where 6 is the chunk here, 6 actions at a time. And then this will repeat. Okay, now here, this is the broader architecture that we would like to have. This is very similar to a variational autoencoder second part, where we pass the latent variable to the decoder and the decoder predicts the next set of actions. But now here you can see that there is a problem here, right? Because these actions will be dependent on the joint angles and also the images from the camera feeds, which we have not yet passed to the to the encoder before. So we need to modify the above architecture, which leads us to architecture version 4, which is the decoder architecture, in which along with this latent variable, we also pass the current observation, which is the current joints, and the information from the camera feed. Remember, during testing, we are going to throw away the encoder. We will only use the decoder. So the decoder should definitely have access to the joint angles and the images from the camera feed, right? Otherwise, it will not be leveraging all the data which is available in the environment. And then it should predict the next set of actions. So this is what the decoder should do. Now let's understand uh, a scenario where a robot arm is positioned to pour coffee, and there are two cameras. There is an overhead camera view and there is a wrist mounted camera view. So you can see the wrist view here is uh, looking at this part of the image, and the overhead camera view is looking at this part of the image. So the robot has two eyes. It has an overhead camera which looks directly at the table, and the wrist camera looks at the coffee cup and the jar which we are using to pour the coffee. Now consider the following situation. The robot is about to pour its arm, and the arm moves over the mug. So what this does is, because the arm moves over the mug, like here, let's say, this overhead camera cannot see the mug anymore because the arm is blocking its view, right? And the wrist camera is the only camera which can see the mug right now. So to understand where the mug is in 3D space, the robot needs to combine the information from both the cameras. So the reason I am explaining about this example is these two cameras are serving two different purposes. The local camera, which is the wrist camera, is understanding these localized movements, and the overhead camera is understanding the overall joint angles. Now, independent processing of this will land you in trouble because you need to understand the 3D contour of the mug and the cup. So you need a way in which you can fuse all this information together. Otherwise, you won't know exactly how the object looks like. So imagine a cube, for example. If you just focus on the top view, a camera which is looking from here, then you will only see this surface of the cube. If you have a camera which is looking from here, you will see this surface of the cube. To get an overall idea of how the cube looks like, you will need to fuse information from the different camera feeds, right? Now, where is the fusing happening in this architecture? There is no fusing. We are just passing this information directly to the decoder. That is why the fusing of information is exactly what an encoder does. And the decoder architecture is modified such that before we pass this information to the decoder, we use another encoder here. Now, this is different from the encoder that we have discussed before. The objective of this encoder is to fuse all this information together so that a proper and a combined representation is passed to the encoder before to the decoder before it decodes the actions. So the objective here is fusing of information. Where have you seen this fusing of information before? Remember when we discussed about the transformer architecture in detail, we saw that there was an encoder here, transformer encoder and a decoder. So if I want to translate any sentence, let's say I am in India and the translation is Main India mein hu, but the encoder first, if everything is passed to the encoder. So the encoder gets a sense of what is the sentence really, and then it is passed to the decoder. So this is also something like a fusing operation which is done inside the encoder. Okay, so please understand that this is different from the first encoder that we looked at. This is the encoder which appears within the decoder of the ACT policy. Okay, so now let's understand how all this information is passed and what exactly happens in this encoder. So please pay a close attention to this part. We'll take a very nice example so that we understand it. So let's say there are 4 images collected from the 4 cameras. We have 4 cameras here. Two wrist camera, top and front camera. So let's say these are the 4 images which are collected from the 4 cameras. Okay, so now what we do is these 4 images are first passed through a CNN, which is a ResNet 18 architecture that reduces the spatial dimension of the image to, so each image is 480 cross 680 pixels and having 3 channels RGB. You convert this to a feature map of 15 by 20 and the dimension is 512. Okay, so the top image, it will be converted to 300 feature maps. The side image will also be converted to 300 feature maps. The wrist and the front, all images will be converted to 300 maps, where each feature map will have a dimension of 512. Now, what is a feature map and how does it look like? So, this is an example of one feature map which looks like this. And a feature map is something which grabs individual features from an image. It is something which is very common in the CNN literature that whenever you pass any image through a CNN, you construct feature maps. So even if you are not familiar with this terminology, it is completely fine. This is an information which you can just consider as something which is an extra information to understand how these images are processed. Okay, so then what happens is these feature maps are all combined together. So let's say one feature map we consider is a 15 by 20 vector and we combine it into a single vector of 300 dimensions. So this is something which I had already discussed, that we combine this so that it becomes a vector of 300 dimensions. And then we have a flattened sequence of where we have 300 feature maps, 300, 300, 300, 300, and each has 512 dimensions. Overall, we have 1200 vectors, and each vector has 512 dimensions. Okay, so just to recap, what we are doing here is we have collected images from our cameras from 4 cameras, but we cannot directly pass them to the encoder right now. We first pass them through a CNN. The CNN converts them to feature maps, and then we flatten these feature maps to convert this into a flattened sequence. What does a feature map do? A feature map is something which understands what is happening in your image, the different parts of the image, etc. Okay, so totally we have 1200 vectors with dimensions of 5 and 2. This is all that you need to remember at the end of the computer vision processes. Finally, we have 1200 vectors, or you can also look at it as 1200 tokens. So this part of the processing is done. Similarly, we have to process these joint angles also before we pass it to the encoder. This actually we did for the previous encoder also, but I did not expand upon it because I wanted to do it over here. So what we do is there are 6 dimensions, right? We use a MLP and project it to 500 dimensions. This is something which I had called embedding in the first description, but to help you understand what happens in this embedding is we increase the dimensions of everything here so that they become 5 and 2 dimensions. So now we have covered all of this. The part before was slightly technical, but you can just consider that as something which comes under pre-processing of the information before it is fused together in the encoder. So in the pre-processing stage, we had 1200 vectors coming out of this of dimensions 5 and 2. We have one vector coming out of this of dimensions 5 and 2, and again we have one vector coming out of this of dimensions 5 and 2. So essentially we have a bunch of tokens. You can just consider that before we use the encoder, we have a bunch of tokens which we want to fuse together with the encoder. Now whatever is going to happen next is exactly the same that we discussed in the transformer encoder and decoder part. Once we collect and pre-process all this information, we need to pass this to the encoder. So to pass this to the encoder, we need to synthesize three types of data. The first is the visual data, which is the pixels or features from the four cameras. The second is the proprioceptive data, which is the precise numbers for the joint angles. And the latent representation, which is a instruction on how to behave. We have already looked at this. This is coming from the encoder side. Now, all these different types are different, and if we just stack them side by side, the model wouldn't know how they relate. And all of them are related to each other, right? Because whatever is coming from the visual data, that is influencing the movement of the proprioceptive data also. So for example, the gripper token, which is coming from the joint data, is linked to the mug handle token, which is coming from the camera one. And this is why the encoder architecture, this has to be a transformer architecture. Because all these dependencies between different tokens have to be captured. If we just use an MLP here, it will not be able to understand that first of all, these images are linked with each other internally also. Because there are four images and there will be some common representations between these images. And also there is a link between these images and the joints. Now, it is very difficult to humanly express these links. I might try to do that, but I might make a lot of mistakes. And so we delegate this job to a transformer. We tell the transformer that your task is to fuse all these images, all this data together, use the self-attention mechanism and fuse the data together. Now we come to the next architecture, which is architecture version 6, in which the only thing we have done is we have replaced this encoder with the transformer encoder. Now, can anyone try to think what will be the output of this transformer encoder? For now, just forget that we are talking about robotics. All we have is a bunch of tokens, right? Remember the example on the translation that we had looked at, in which this I am in India was passed through a transformer encoder. What was the output of this? Okay, there are several answers. Next state, next action. Okay, forget about this question. Try to answer this question. If the input is I am in India and I pass it to the transformer encoder, let's not consider CLS token for now, but let's consider just this as our main input. Cross attention, first word in translation, embedding. There is a specific terminology which one person in the chat has got it correct, but I want everyone to understand what is the output. Yes, exactly. There are context vectors is the output. So the output of this is the 4 context vectors corresponding to the tokens which have been given as an input. Now, once we understand that, okay, fine, what is happening in the transformer encoder is it is doing an attention mechanism inside and it is calculating the context vectors for all of the tokens which are passed as an input. Now, how many tokens we have for our robotics example? We have 1 token for the joints. We have 1 token for the latent variable. And we have 1200 tokens for the images. So totally we have a bunch of 1202 tokens. In this example, there were 4 tokens. I am in India, but in this case, we have a bunch of 1202 tokens which are passed as an input to the transformer encoder. And so naturally what we will get is the output of this will be 1202 context vectors. Now this is something which is very interesting because the first time you look at it, all of us are used to thinking of tokens in the sense of LLMs, right? We are used to thinking of tokens which correspond to language. But images can also be considered as tokens. Joint angles can also be considered as tokens. Latent variables can also be considered as tokens. Once you understand that, it becomes very simple. Then it only boils down to your understanding of the transformer mechanism. Because everything else is going to stay the same. The only difference is how do you construct the tokens out of your input. And here the only complex step was how do we construct the tokens out of these images? For example, how does one image map to 300 tokens? It almost feels like this step is a bit non-intuitive, right? Why do they consider this feature map of 512 dimensions? We can understand because everything is converted to 512 dimensions. But why do you have this 15 by 20 in the feature map? And I would like to make one correction here, which I probably said it in the reverse way. I think I said that there are 300 feature maps here. So the correct representation for this is one feature map has a dimension of 15 by 20 and like this there are 512 feature maps. So how do we create 300 tokens out of this? 15 into 20 is 300. So each of these individual blocks can be considered as a token. So basically you imagine this and imagine that each token is this cuboid. So like this, there are 300 tokens. This is how every single image which is coming in from the camera feed is converted to 300 tokens, where every token has 512 dimensions because there are 512 feature maps which are there in this process. Now, this we can understand. You choose to construct 512 feature maps because every feature map tells you something different. Like, for example, this is what each feature map does. But then on what basis was this 15 by 20 selected? This is something I think it can be varied. You can change these dimensions based on uh, your preference. You can maybe make it 10 by 10 or something. But I think they figured out that this combination, which is what leads to 300 tokens, performs the best. Yeah, so as Pramod says, you simply flatten it at the end and you generate these 300 tokens. Once you understand this, that 1200 tokens for this one, we have only 1202 tokens which are passed as an input to the encoder. And finally, what you get as an output is the 1202 context vectors. How are these context vectors generated? You create queries, keys, and values for these 1202 vectors. You do a self-attention scores queries into keys. You multiply these attention scores by the values and you get the attention output. And finally, you pass it through a feed-forward network, which becomes the output of your encoder. What does the latent variable Z correspond to here? This is the input which is coming in from our encoder side. Remember the first encoder that we saw? We are producing a latent vector out of this at the end, which is capturing the different modalities of doing the same operation in the human demonstration data set. So this latent vector is coming from this encoder and which is passed as an input to this encoder, to the second encoder. Okay, so under the hood of this is exactly what is happening. In case some of you are still confused about queries, keys, and values, please have a look at the last lecture in which this is explained in a very comprehensive manner. The same thing keeps repeating multiple times. As you saw in the previous, in this lecture, we have repeated this 2 times. And it's the exact same architecture. So once you become comfortable with this architecture, you can see that it's repeated every single time. And this happens not just in this paper, but in a lot of other papers also. So it makes sense to spend a lot of time in understanding the transformer architecture. Okay, so I have tried to help you visualize this in the format of a video. Let's try to see if... Okay, so I'll be pausing this video from time to time. Okay, so 4 cameras, top, side, wrist, and front. And the first step is to extract features using ResNet. So once the features are extracted, this part I have deliberately skipped. You add positional embeddings also. So you have these 1200 tokens coming from the images, one for the joints and one for the latent variable. You concatenate them and you get a total of 1202 tokens. Each token has a dimension of 512. Then you pass it through the transformer encoder layer, which is a self-attention mechanism and a feed forward layer. So what happens in the self-attention mechanism is this. Every token projects to Q, K, and V. and you form these attention scores where you understand that, okay, so the gripper is attending to handle, or camera one is attending to the handle, etc. So this is the part where the attention mechanism within the encoder is fusing all the information together and understanding how the different parts of the robot and the different parts of the environment are connected with each other. And I think this is where all the intelligence gets fused, and this is the most important part of the policy. Then it is simply multiplied by the value vector, and you get the final context vectors at the end of it. Then it goes to the feed forward network where you expand it and then you project it back. Okay, so now let's go ahead. Once we have the output of from the transformer encoder, we can actually connect it to our final decoder and we can predict the next set of actions. Now we will again be looking at or referencing our discussion on the transformer decoder in the previous lecture. What happens in this decoder is very interesting. We have a cross attention layer in the decoder which attends to the keys and the values which are coming in from the encoder. So the decoder or let's okay. So let's look at the decoder very closely. So the first step in the decoder is these are the 6 positional embeddings which we have fixed. Okay, so I will explain about this later. This is very different from the transformer decoder that we have looked at in the last lecture. But for now, just assume that these queries are available to you. So there are 6 queries. In the transformer decoder, we just pass one query right at a time. Like let's say, मैं India में हूँ. So this is passed as a query, this token. But in this case, it is slightly different. We are passing 6 queries because we want to predict 6 actions at a time. So we have no other option. Okay, so there are 6 queries which are generated at the beginning. But what about the keys and the values? So let's try to understand that. So the 1202 keys and values are coming in from the encoder side, which is the output of this. So there were 1202 context vectors, right, which were generated as an output from the encoder. These are used to calculate the 1202 keys and values, which are shown over here. And then we perform the cross attention. So we have the 6 queries here and the 1202 keys. We calculate the attention scores and then we multiply it by the values. And finally, for each query, we get the context vectors at the output. So now let's again revise what we have done here. There are 6 queries here because we want to predict 6 actions at a time. Every query is attending to 1202 keys which are coming in from the encoder side. We are calculating the attention scores and the attention metrics. This is multiplied by the values which are again coming from the encoder side. And we get the final context vectors for all the 6 queries. Now we pass these through an MLP layer, and again we get the final context vectors at the end of it. So now you might be thinking, okay, this is great, but these context vectors are having 512 dimensions. How do I generate 6 actions at the end of the transformer decoder? So how that happens is, for every query, these 512 dimensions are then projected to 6 joints. And this is done for all these 6 time steps because we want to predict 6 actions at a time. So for first time step, we predict the 6 joints. Then for the next time step, we predict another 6 joints. Then for the next time step, we predict another 6 joints. And this happens for as many number of times as the number of chunks that you have, number of action chunks. Now, if you compare this with an LLM, we had a projection layer, but we projected into the vocabulary space, right? Where we were predicting the next token. So here we are not projecting into the vocabulary space because we are not predicting the next token as such, but we are projecting it to 6 values because we want to predict the 6 actions at the next time step. And this we want to do for the total number of action chunks. So that is why I have done this for 6 times. Okay, so now this part, which I very quickly mentioned, that there are 6 queries which are generated. This is inspired from a paper which is called as detection transformer. That is why at the beginning I told you this was one of the innovations in the Act policy. Now we will not very deeply understand this, but the only thing I want you to very nicely appreciate is we are predicting 6 tokens at a time. We are not predicting 1 token at a time because the action chunk is 6 here. And that's why everything else is same here. Encoder, decoder, every single thing remains the same. The only difference is that we are passing these six queries which are actually fixed. This does not vary at all. What varies at every time step is these images and these joints. That's why we get different actions at every time step, but the queries, it remains fixed. So you can look at this detection transformer paper if you have time, but let's look at the architecture so that you understand how it is inspired from Decoder. So here, this is what detection transformer does. Here you see there are these object queries which are passed 4 at a time in this case. That is exactly what we have done here. Another word for this is also object queries, but that word is uh, explained in the detection transformer paper. Here we are just passing these 6 queries at a time and we are predicting these actions. And then if you combine this entire architecture together, you get the final architecture for the ACT policy or the ACT variational encoder. So the first thing that we started with, our discussion started with, we will use a variational autoencoder in which there will be an encoder and a decoder, right? So then we started discussing about just this part, which is the encoder in the variational autoencoder. Then we discussed about the decoder. Now the interesting thing is that the decoder in ACT policy also contains a transformer encoder because we want to fuse all this information together. How does this fusing happen? We looked at this corresponds to 1200 tokens, this corresponds to 1 token, and this corresponds to 1 token. So overall, there are 1202 tokens which are passed as an input to the encoder. And these are the context vectors. Now the input to the decoder is not just one single token, but these chunks of token, which is inspired from the Decoder architecture. And then at the output, we get these, let's say we have chunk size of 10 actions at a time. Okay, so what we will do is I have prepared some list of questions to ask all of you to make sure that we also revise these architecture and also understand the concepts better. So the first question is, let's start with this. Why do we pass the joint positions as an input to the variation autoencoder? That is, here, why do we have joint positions? To understand the current state. Both of you are right. Without the joint position, we will not understand how or on what are the actions conditioned on. Without the joint variables, we'll just learn the probability distribution for the actions. But these actions are always conditioned on something. And that is why we need to have the joints over here. The second question is, why do we have a CLS token over here? So Sri Harsha, Yashwant and Vishaka all are correct. The CLS token is actually containing the summary of everything. Yeah, Preetham also and Pramod are also correct. We need to have a variable which contains the entire information, which contains the style in which you are performing your actions, the style in which you are moving the robot to achieve the task at hand. And that is captured in the CLS variable where the output is generated only looking at the CLS context vector. Okay, the next question is, why do we need a transformer architecture for this? Why transformer? Why don't we just go for a multi-layer perceptron? Yeah, so everyone is correct. We want to model these sequence of actions. So we want to capture the dependencies in these sequences. That is why we need an transformer encoder over here. Now, something that is non-intuitive is, why do we have an encoder in the decoder? So, in other words, you have two encoders over here. What is the purpose of this encoder? Okay, so exactly. So all of you are correct. Sri Harsha, Ajiket, Pramod, Preetham. So it is needed to basically use all the information which is coming in from the four cameras as well as the joint angles and the style variable. If you remember our first discussion on classical robotics, we had said that one of the biggest problems in classical robotics is it cannot handle multiple modality. There is no way in which we can represent information coming from different modalities like images, text into a common representation medium. And that is exactly what we have done here. We have represented all as a bunch of tokens and created embeddings for all of them, which is one of the main advantages of AI or modern robot learning is you can have information which is very different in terms of the modality, but then you can represent it through a common representation scheme. And then you can learn relations between these representations using a transformer architecture. So this fusing of information is in fact very common. You will see it in other modern policies as well. Okay, now this is something I have not touched upon, but why do you need position embeddings here? Can anyone explain this? So which order are we planning to capture here? The order matters, but what are we trying to order? So we want the, yeah, exactly. We are learning the action, the order between actions. If there are 10 actions, if we do not pass the position embedding, then it can learn the distribution of the actions for every joint. That is fine. But what if it generates action 8 first, then action 9, then action 1? That is something we do not want. We want all these actions to come in a sequence. First action 1 should come, then action 2, and then action 10 should come. And that is why position embeddings are absolutely crucial. Otherwise, it will definitely learn the probability distribution, but it will not be able to follow the specific sequence. That's why you have this position embeddings written over here. Okay. So I think broadly we have understood the overall architecture, and we have learned how the Act policy works, the different components within the Act policy. What makes it unique is the use of a conditional variational autoencoder. Second is the use of action chunking. And third is the use of a debtor style decoder where it predicts multiple actions at a time. And this is on the software side. On the hardware side, uh, it was the first time it showed that low cost hardware can be used to generate these policies. Now I think you can understand these 3 points which we started in the beginning. It uses a conditional variational autoencoder. That was the first. It uses a debtor inspired transformer, and it uses action chunking. So all of these you should be able to understand now. And one of the best homeworks that I can give to all of you is take a printout of this paper and actually read it completely. I think you will be able to understand the entirety of the paper now because we have almost covered all the intricacies in the paper. There is one small thing which I have deliberately not covered, but I want you to look at it and explain it to me in the next lecture, and that is temporal ensembling. Okay, my pen is not working, but This is the only part which I have not touched upon. But please have a look at the paper, and the best way is to download it and take a print and read it and make highlights in the paper. There might be some things I have missed in the discussion, but those things you will understand when you read the paper thoroughly. And once you understand the Act policy, as I explained before, you will find it much easier to read other robotics papers as well. Okay, so now as we discussed, one of our main focus in these boot camps is going to be to implement this Act policy on a robot. But before we do that, we need to understand how the Act training is done. So far, we have looked at the Act architecture, but how is the training done exactly? Let's try to understand that. Okay, so first you define the chunk size and you initialize the encoder and the decoder of your architecture, then begins the training loop. We are assuming that you have access to a demonstration dataset already. This is the dataset which is recorded by humans, and it is a set of trajectories. So for the current experiments that we are doing, we are either recording 10 episodes or 50 episodes. I think in this paper they have recorded 50 episodes. Yeah, 50 demonstration trajectories. Yeah, we recorded 50 demonstrations for each task. So basically you have 50 demonstrations, or it depends, you can vary this number as well. And then what you do is you first look at the joint positions and the future action sequences for every time step. This becomes an input to your encoder. What does the encoder do? The encoder takes these states and the target actions as an input. It passes it through the transformer architecture, and you get the probability distribution, that is the mean and the variance, and then you sample the latent variable. So just as an example here, you look at time t equal to 0. You have 6 joint positions. And if the chunk size is 10, then you have 10 set of 6 angles, so totally 60. And then this is passed as an input to your encoder, and you get a sample variable at the end, which is the latent variable. Now what you do is you pass it through the decoder. Now this time the input to the decoder is this latent variable, the joint state, and also the images. Then you pass it through the decoder network. Remember, this is 1202 tokens over here. And then you get the actions which are predicted from your decoder. Now, initially, these actions will be very different from these actions. So there will be a loss term which you try to minimize, which is called as the reconstruction loss. Now, in our discussion on variational autoencoder, I had also emphasized on the second loss, which is regularization loss. And what does the regularization loss do? Can anyone explain this if you remember it? Normalizes the loss values. No, it is something different. It is something related to the latent variable actually. Vishaka is correct. Can you expand more? Which distribution is this, which we are forcing it to be Gaussian? Yeah, Vishaka, Sriharsha, both are correct. Uh, we are forcing the latent variable to assume a Gaussian distribution towards the end. And this is something which has proved to be very useful in the variational autoencoder setting. The reason is that we expect most of the distributions in the real world to follow a Gaussian. And that is why this regularization loss is added so that this is your latent space of 2 dimensions. Then you force everything to be concentrated with a mean of 0 and a variance of 1. And then you get the total loss, you update the weights, and then you perform this loop. Now, all that we discussed in these 4 lectures was designed for you to understand this training loop. And I really hope all of you have understood what happens in the ACT training, why it is an example of imitation learning, because we are showing these expert trajectories and we are learning from them. Why we are using a variational autoencoder in the first place is because point estimate policies fail in imitation learning. They do not capture the different modalities. And that is exactly why the variational autoencoder framework is used. Why did we discuss about transformers? Because they are at the heart of the entire architecture. There are 2 transformer encoders and 1 transformer detector, 1 transformer decoder, which is used in the architecture. And now all of these comes together very nicely in the entire training loop of ACT. Now, one of the experiments, or for people who are curious, can go to this learnable GitHub repo, go to policies, go to act, and go to this modeling act.py. You should be able to understand this entire code now because it is exactly based on this architecture.